Yeah, it's great that Benny already introduced the main topic, so I can go quickly over this connection. But I think it's a really exciting time for us quantum information theorists to start talking to these new branches of physics, and these branches of physics that are looking to talk with us. So I changed a bit the title of my talk, so I was going to talk about towards holography via quantum source channel coding, and I want to give a more general overview because I realize that the focus in this conference is mostly not on this connection with physics and specifically with holography, but with quantum computers. But first of all, I want to thank my collaborators. Benny Yoshida is here, John Preskill is here, Daniel Harrow, who was here on Monday, and the people from Berlin, Jens Heisert and Henry Wilming. So, okay, so as I said, what I'm going to talk about is not quantum error correction with focus to quantum computation, but with focus to understanding physics. And this has been sort of something that I've used throughout my study in quantum information. And the reason is that if you have any robust phenomenon in physics, then it should be protected from some noise or spurious effects. And this happens for, and we have a lot of connections. So code subspace, we've come to interpret them as ground state subspaces of Hamiltonians. Symmetry breaking can be understood as some classical form of error correction. Topological phases of matter connect to topological quantum error correction, which actually brought us a revolution in quantum coding. I mean, more than half of the talks in this conference are about topological quantum error correction. Thermal stability, one can connect to self-correction. Robustness of specific observables instead of subspace, one can describe with operator algebra quantum error correction, something that I think we should be hearing more about, but it's not such a big issue right now. And there are these new connections that are coming from a suggestion that came 3 years ago from people working in holography, trying to figure out quantum gravity. And they're essentially suggesting that also conformal field theories, so some special form of critical quantum theories, should be connected to a new form of error correction called holographic codes. And and there are similar connections. So bulk flow energy sector, now not ground state, not degenerate ground space because there is no degeneracy, should be connected to some coding notion. And what I'll talk a lot about today is about holographic geometry and how this can be translated into code properties. So, but first let me sort of briefly recap what the motivation for these people are that came eventually 3 years ago to talk to us quantum error correction people. Well, they want to marry two theories, the most successful theories in physics. Quantum mechanics, which is summarizing just based on superposition and unitarity, and the theory of general relativity, which couples mass attraction with the stress energy content in space. This is a geometric theory of space and time. But there seems to be some trouble about matching the two theories together. And I'm going to give a sort of the first puzzle about why this puzzle comes. And it comes where you have the titans, where the two theories act at their strongest, and this is in black holes. Black holes, according to general relativity, are supposed to have an area uniquely specified by their mass, and, well, no hair. They require very little parameters to describe them besides the mass and some charges. So essentially, the puzzle comes from information loss, because quantum mechanics preserves information, but if you throw something into a black hole, then it disappears. It just comes back as noise. Well, maybe it was noise. So there's an issue with the second law of thermodynamics. And the first time that people proposed a resolution, it was sort of proposed at a formal level. It was Bekenstein and Hawking. And they said, okay, what if we assign a formal area to these black holes? We'll say, okay, the area of the black hole is given by this, and we'll assign a formal entropy to it. such that you don't reach any contradictions, like when two black holes merge, you don't have entropy disappearing. You can have conservation of information. But as modern quantum information theorists and modern physicists, we know that entropy, this thermodynamic concept, is just an information concept. It's just the number of microstates divided by some weight. So I think this step was really revolutionary in that it's getting rid of units in physics. It's getting rid of the units of area. Just like previously in Einstein's general relativity, time and space were related by the speed of light. Now you're really getting rid of these units of area. 1 meter square is 10 to the 69 bits, or e-bits as you'll see. It's a huge number, but they're gone. And that means on this side, us quantum information theorists can work with it. Okay, but it took some time for these concepts to seek in, but eventually they found a place in holography, because the notion was that you cannot pack more information than the area of a region. So maybe the information is actually encoded in some screen. And that's the theory of holography. They say, okay, we live in a gravitational space. That's how, I mean, we live in both because there's an isomorphism, but we describe it in this gravitational way. This is what's most convenient to us. But apparently, there could be some fully quantum theory in a boundary space, in this case, this blue ball outside, which doesn't have gravity, it's just a field theory. And their unitarity is explicit. Okay, so what are these black holes? Well, in this language, black holes are like balls of the thermal entropy, and you have excitations in the bulk. They also correspond to, in some form, to excitations in the boundary. And okay, this is the ground for where this connection with quantum error correction comes, and what Daniel told us about. So let me line it out. So what does quantum error correction have to do with holography? Well, the first thing that got us really on board was this bulk to boundary locality, and this paper by Ahmed Almeri, Kai Dong, and Daniel Harlow, which came out a bit more than 3 years ago, just before the last QEC. And then we came up with some tensor network models, and the point is that they need quantum error correcting properties, but the structure of their system is not tailored to our run-of-the-mill stabilizer codes or gauge subsystem codes. So we really need to work hard to fit with that, and to sometimes match very counterintuitive expectations that come from there. Okay, so let me explain what bulk to boundary locality is and how it fits with erasure correction. Well, the best understood model of holography is this ADS-CFT. So ADS-CFT is this kind of soup, as Daniel or Susskind would call it. So the gravitational theory is in the bulk. So there's an arrow here. So this upward is time. And these disks here are constant time slice. And inside you have a theory that has gravity, that you've described through gravity, things with mass attract themselves. But at the boundary, there's a completely equivalent theory which doesn't have gravity, just has fields. But the point is, because in gravity, in general relativity, you can study the system in different reference frames. You can evolve the equations of motion such that they don't look at the whole system, but just as a part. This is an accelerated reference frame. And sort of one of the ingredients of this holography was that when operators in the bulk go very far towards the boundary, then they actually correspond to operators in the boundary. And this is what one does when one does this evolution in this slice. One evolves, one thinks, okay, I have some operator here in the bulk. I evolve it all the way such that it falls in the boundary, and then now I take the boundary evolution and I evolve it back. So now everything is happening in the time slice. I have some bulk operator, some quantum, I don't know, string theory. I mean, this I will not understand because I don't understand general relativity. I don't understand string theory, but I understand this expectation that there should be something like an operator here, and it should be mapped equivalent to something in the boundary or in a piece of the boundary. And I can choose this geometry in different ways, and this leads to different pieces of the boundary where I can represent the operator. In particular, let's say I have the operator here. I can represent it on any two regions, but I don't get any signature if I just look at one. So this is like saying, I can map the operator to AB, to BC, or to CA. This is the puzzle posed by these people, Ahmed, Guy and Harlow. And the resolution that they propose is, okay, this is essentially like quantum error correction code. Why? Well, the fact that you can reconstruct an operator in a pair of regions means that you can erase this region, and you're still fine. You can still recover your information. This is why the erasure noise model is natural for their setting. So now let's do a dictionary between holography and quantum error correction. So in the holographic language, you have these bulk operators. So these are the operators that I would like to understand better, which live in the bulk. And in the quantum error correcting code language, they correspond to logical operators, things that we'll be able to represent in several different ways. And in this case, will be protected from noise. Boundary operators are now the physical operators. So this is their ADS-Rindler reconstruction. This is this reconstruction that I showed in the slide before that allowed us to take a minimal surface, or in this case, in 2D, it's actually a geodesic, and take one side of it, and if the operator in the bulk lies to that half, then you can represent it in this, say, green, the boundary of the green plus yellow region. If you take this other one, you can represent it here. And if we consider codes, then there are several codes that have this kind of property. In this case, this is sort of trying to represent a tensor description of what the 5-qubit code would do. You'd have an input qubit lying here at x. And now it's a 513 code, which means that you can delete any 2 qubits and still represent the operator. In particular, I could delete these 2 and represent the logical operators here in these 3, or in these 3, or in any 3 that I want. So particularly, this is something called a perfect tensor, which means that it's an isometry no matter how I look at it. This is, I can think of it as a one bulk leg coming in and 5 other legs. And we use this property to actually build tensor network models of these holographic codes that qualitative, more or less, they hide this property. I mean, if I had some operator here, now I have a tensor network, these tensors are connected. If I have an operator that I want to reconstruct somewhere in the network, I can look at some of these patches and I can reconstruct it either here or here. So there's some form of bulk to boundary locality which is preserved, and this is qualitatively similar. And let me sort of explain how reconstruction works. Well, if you have access to a certain piece of the boundary, you have a systematic way of reconstructing part of the bulk, which is like a rubber band. And you look at the tensors that you have, the tensor indices that you have access to. And if there's a tensor for which you have access to more than half of the indices, then you say, okay, I can undo that tensor because it's an isometry. I can undo it. I can treat it as a unitary maybe. And then you progress. That means that you have access to a layer of indices which are deeper, maybe some bulk indices directly. You continue. This is what we call the greedy algorithm. You can think of it as a rubber band which is contracting as long as it tries to find locally a minimal surface. And at some point it gets stuck. It doesn't see any other tensors for which it has more than half of the indices and can't progress further. That means that we could have reconstructed the bulk indices in this region, but probably not the ones in that region. So this is, again, a qualitative reproduction of this Rindler wedge reconstruction. Okay, what's the other property from holography that should be relevant to us quantum information theorists? It's this holographic area law. So let me go back to entanglement scaling. So we have different kinds of entanglement scaling. If you pick a Hoare random state, this is what Page did in this black hole experiment, what you would expect is that the entanglement of a subregion or as a subset of qubits is proportional to the dimension of that subset until you reach half the system size. This is what we would call a volume law for entanglement. In local physical systems where there's a gap, we've come to expect and even proven in 1D systems or certain cases that we won't be seeing an area law for ground states, but we'll be seeing a volume law, but we'll be seeing an area law. So the entanglement, say if I consider the reduced state of the ground state on this blue region, will not be proportional to the volume, but to how much the boundary is with its complement. And there are several constant correction factors, and we should look into this. This leads to topological ordered systems and such. But yeah, already this allows us to do things in terms of quantum error correction, and I think Michael Castoriano will talk a bit about this in the context of approximate quantum error correction. But there's something in between, something where the states have some entanglement structure, but it's not really the area law of the system that you have. And this is what Ryu Takayanagi proposed as the holographic area law. So the Ryu Takayanagi formula is, well, I was looking at these hyperbolic cylinders where the metric was this lizard metric. So it's actually, the minimal surface is not going like this, but if I do like this, I cross less lizards. So now the minimal surface, the entanglement, is not the area here, which would be, say, constant, this plus this, but it's this area. So one can think of this in two ways. One starts from the geometry and posits the entanglement, or maybe there are certain states that actually lead to a geometry. So this is one of the ideas that's being pushed very hard in this community is geometry emerging from entanglement. And again, sort of the prefactor is the same one that appears in the Bekenstein-Hawking association of entropy to a black hole, but this time it's entanglement entropy, and this is like a massive generalization of that idea, which has been checked in CFTs, but we can sort of we'll try to extrapolate it further. Okay, but why should we say that this is conductive to quantum error correction? I mean, at this point, it's just entanglement. But, okay, so first of all, let me mention that in this toy model that we could also reproduce sort of in tensor networks, entanglement is always upper bounded by these minimal cuts. So minimal cuts are now analogous to minimal surfaces. But in this case, if we put these special tensors, the entanglement saturates this in certain regions, in contiguous regions. So yeah, maybe also let me recap some features and bugs. So we have some exact quantum error correction properties. Now the code, this tensor network represents an isometry, not an isomorphism. And for the theories, we expected an isomorphism. We said that the theory should be isomorphic. There's no continuous time dynamic. That's a bug. We have an exact holographic area law, but actually, if we talk to holographers, we'd say that they would say that they don't expect it to be exact. And by doing this exactness, we've discretized boundary correlations. We can reproduce some bulk or boundary translation invariance, but not the full boundary translation invariance. So, I mean, it reproduces some features, but it's a toy model, right? So, we'll get back to this. And particularly to this, the isomorphism. But first, let me mention why this holographic area law is really important and should be taken seriously in quantum error correction. Well, the reason might be reduced to this quantum Markov condition, which is, yeah, I guess Michael will talk about it more. Which essentially tells, okay, this is the conditional mutual information. This is a specific combination of entropies. And it tells me that if I have a state for which this is 0, then I have some recovery operation, some map, which recovers from the erasures of C. So this map looks at B and reconstructs BC. So if I lose C, I apply this map, I get back the whole system. So I can locally recover from some erasure error or from some noise if I know that the noise occurred here. And this is a condition which is purely based on entropy. So if I have an area law, a holographic area law, what I can ask is this condition true? So I can say, okay, let's say that B is the sum of these two regions. Now, the entropy for B can either be this area plus this area or this plus this, depending on how things are connected. But if I get that it's the entropy for B is this plus this, sort of entropy of B is equal to entropy of C, which is here, plus entropy of BC, which is this one here, then this is essentially the simplification of this conditional mutual information being 0 for the case that ABC is a pure state. And And in general, if I have a tensor network and I consider all these indices as indices for the state, I can think of it as a pure state. And what we will think is that a manifold is encoding a pure state at the boundary. So okay, so I'm getting these reconstructibility conditions just by looking at entropies or just by looking at the holographic geometry that emerge from this. Not all states admit a holographic geometry, by the way. This is a very special property of states. If you look at a flat geometry, like what's going on here, you need to compare, okay, is the sum of these two entropies, these two lengths, smaller than these two? If it is, then that means that you can reconstruct this C by just looking at these two guys in the state that has this holographic geometry, and so on. But I mean, in the flat case, the conclusion is that you would actually need a much larger buffer region for a loss here, C, if you have a small loss. But anyway, the point is that using the Markov condition, we can go to quantum error correction. And we can look, okay, so suppose I have two regions, and I want to be able to correct this. If I can correct this by just looking at that, then I can use the previous construction to reconstruct any point operator that was here. I can reconstruct it on this region because I've been able to reconstruct it. And sort of this is the regime where things look like that, where this is the minimal surface. This is the regime where this is the minimal surface. And in the hyperbolic case, because the entropy is logarithmic in the size of the boundary region, so this is specific to when the holographic geometry is hyperbolic, or this case of an ADS-CFT slice, you get a condition like this, which is simple. You can match R1 and R2 to be the same, and then you figure out what's the size of the largest hole, or the size of what's left after you punch a hole, and you get that the size is roughly 82%. So if you keep 82% in these regions, then you can punch a hole and still recover from it. And this is something that we discussed in a paper with John. And the point is that you can do this procedure, because this is a local reconstructibility, you can do this over and over again. So suppose I have some operator in the bulk that I want to reconstruct. Well, first of all, I can use this Rindler wedge reconstruct and say, oh, I can reconstruct it on this region, by the way. But this region, if I lose part of it, because of this entanglement holographic rule, I can reconstruct this from these two guys, and that will be fine. But each one of these I can reconstruct from these two guys, and that'll be fine, because I can punch a hole again. And by doing this, I'm constructing this kind of this Cantor-like set, which has a fractal dimension. And it's a fractal dimension of 0.786. And this is a universal thing for this uniform negative curvature. So what are we calculating here in terms of codes? Well, this is sort of like a distance, right? This is, and we proved that this is the minimum piece of the boundary, or that you need in order to get a point in this entanglement wedge, in this, if the minimal surface is going to keep it inside. So this is kind of a distance, but it's something else. It's not really a distance. It's telling us that we can represent the operator in this fractal region. And this brought us to actually think a bit harder about, okay, what is quantum error correction and what are the quantities in it? And in quantum error correction, you actually need to balance two things. On the one hand, you want to protect information. You want it to remain accessible despite some noise, some loss. But on the other hand, you want it to be quantum. And if the complementary information is too readily accessible, then the environment can access it, and you lost it. So you also need to hide the information. If you don't hide it, then the environment accesses it, and the complementary part gets lost. So this is what we call the no-free. So these two things get quantified in different ways. So one is the distance. It tells me how much you can lose, and you can still guarantee that you can recover the information. Now I want to refer to it as some subalgebra of the information that I care about. So say one logical qubit, for example. And say if I lose less than d qubits, then I can recover that algebra. But there's a different notion, which is the price, which is how much do you need to access in order to read out part of that information? And these might be, in general, different quantities, that they're not related, in particular when this algebra is abelian. But if this algebra is non-abelian, then you have this trade-off, which we call the no-free lunch, which is, okay, if you want to be able to represent this full non-abelian algebra in a region, that means that you can mess it up in that region, because it's a non-abelian algebra. You have some observables that anti-commute with operators. So then for any algebra, price of that subalgebra in your code space is larger or equal than the distance. And this is a generic property, even though, I mean, we started thinking about it from holography, but it's a generic property. And holography seems to be fine-tuned in such a way that these two, this trade-off that you need to make is somewhat optimized. So you're optimizing redundancy and secrecy in a way that if a region R can represent your local algebra of a point, then it's completely inaccessible to a complement, and vice versa. So this is the geometric interpretation. It's admittedly idealized. I mean, we don't have an explicit model for that, but it's the expectation that these people have in large N, large CFTs, or large C. And for points, so if you have an algebra associated to a point-like operators, which actually don't exist in quantum gravity, then the price and the distance are the same. So geometrically, they need to match. And since entropies are associated to area, and points don't have area, then we say that they have zero. But you can take a epsilon sphere at a point, and then this changes the story. Something else which we obtained by thinking about this geometrically is what I would say is a strengthening of the singleton bound. We've proved it for subspace codes and from operator algebra codes arising from this holographic setup. And there, sort of K would be morally the number of logical qubits and logical quantum degrees of independent degrees of freedom. P is the size of the minimal region you need to represent them, or in units of entropy, the entropy that that region can support. The distance is similarly. And we have this inequality, and this actually, together with complementarity, it actually implies the quantum singleton bound, so it's stronger. In its proof, we actually use strong subadditivity, or the holographic version of strong subadditivity. So yeah, I think it's actually pretty cool to try to look at what these people need and see how we adapt our tools in order to make it fit in our boxes, our quantum error correction notions. But there was one thing that I was still not fully satisfied with, and this is the notion that this ball-to-boundary correspondence should actually be an isomorphism. So I was thinking, how can an isomorphism arise? And this rise to the second project, which is the one which I titled. Oh, shoot, I'm missing some letters. But I guess you can figure out what's going on in there, right? You know this game. What letter goes in there? Anyway, so the point is that information, we're constantly encoding information, but we just don't realize it. I mean, here I lost a bunch of letters, but you know what the title is. It's because our language is endowed with so much redundancy that we don't need to put an additional error-correcting code on top of it. So, but how can it be endowed with redundancy? I could have written anything. Well, you don't expect me to write anything. I won't write just some garbled message. And the point is that you have a prior. You have some expectation of what's going to come. And that's why we should actually think of combining channel coding and source coding, which is compression. So channel coding, if I give you the first textbook example, if I want to encode in a subspace, I want to encode k qubits, what I'll do is I put n minus k ancillas, I'll run it through a unitary, and I'll get an output encoded state where it's protected against some local error, maybe some loss error, depolarizing noise, whatever your noise model is, you sort of add some extra degrees of freedom, which you know, and then you can try to guarantee some protection. Now, source coding is compression. You had a large message, you try to get it to fit in something small. How do you do that? Well, Shannon said, okay, you needed to look at the entropy distribution of your state, and if you have many copies, then you can put it without much loss in n, the number of copies times the entropy of distribution of your state. This is a classical result. The quantum result also holds by Schumacher compression. But in this case, there's a difference. We'll be doing one shot, and normally, so you have this compression unitary. What it does is if you have the diagonalized density matrix, it sorts the eigenvalues such that here you have the most significant bits in the sorting, so they're essentially based to 0. These are the ones that you can throw away because you know that they will be 0. And these contain all the information. This is your compressed file. So morally speaking, you apply your compression and you get some ancilla state times some zip file. It's not completely correct, but more or less. And we know how to do this. And this is for the density matrix. So one observation is that actually this same procedure that is doing the compression is actually doing algorithmic cooling. It's producing ancilla bits here. So if you look at it and algorithmic cooling, it doesn't care much about what's happening there, but it tries to get as much purity in that state. And you started with this state that doesn't have the very concentrated purity. So we have some message which has some structure. I won't send you garble. I'll send you an English text that makes sense. You're compressing it, and we were throwing away these very nice ancilla qubits. So why not put them together? I mean, why not do unitarily reshuffle your message such that it's better protected for your specific error channel that you're expecting? And here, I mean, we don't have to. No, you don't need to match the dimensions, but we can match the expectation of holography and really having an isomorphism. And we can increase in a controlled way the source dimension, the target dimension. They'll be the same. You'll maintain the isomorphism prescription. And you can still keep some error correcting properties, and you'll be using this redundancy of your expectation. Sort of this thing was actually realized by Barnum and Knill, so one of our referees pointed this out, and I acknowledge, I think that. But what I would like to point out is that this is interesting to look at it in the context of holography, because then this allows us to get this isomorphism back. So now how do we benchmark such a code where we have assumed an input distribution? Normally we use the diamond norm and say, okay, what's the worst case? What's the worst that can happen to my messages? But now I really have a prior over what states I'm going to prepare. So I'll say with probability mu of psi, I'll prepare the pure state psi. I could have had density matrices there. And this represents the reduced density, the ensemble distribution for the full state that I'm preparing. So one natural thing to look at is the average fidelity. I can say, I prepare these states with this probability. I let them run through the channel, which is now my noise channel combined with whatever I will choose as my recovery channel. And I try to see what the fidelity is of this thing with the initial state that I prepared. So this is called the weighted average fidelity. Now, classic result in quantum information, this weighted average fidelity is actually bounded by the entanglement fidelity, which is take a purification of this guy, any purification, you pick, and apply the channel on one side of the purification because it's the same channel. On the other side, you apply the identity, and you take the fidelity of this guy, this purified guy. So this is the definition of the entanglement fidelity. And the entanglement fidelity is actually a bit smaller than that. I say a bit, well, it could be a whole lot smaller, but if I have a uniform distribution over a Hilbert space of dimension d, then it's only a factor 1 over d smaller than this one here, or up to a factor 1 over d. And this thing here, I can bound, because I can say, okay, I had my distribution, I take my purification of choice, and now I apply this kind of quantum Markov condition. And these quantum recovery map tools that are recently been developed and strengthened so much for the approximate case. So if A is actually a purification, or whatever I needed to add to A was a purification, then this term is 0. I can simplify this expression, and I don't need to look at all those three entropies. I just need to look at the physical system, which is B and C. And I can say that this conditional mutual information bounds to the logarithm of this, in this case, it's, yeah, I think it's entanglement fidelity, but in this case, rho ABC is, we're taking it to be pure. So if I can give it a small upper bound, so now small needs to be really smaller than 1, to this quantity here, I can say that the entanglement fidelity is large, and hence the average fidelity is also large, very close to 1. So now where do we apply this? Well, Benny said that black holes are the best storage of quantum information, so let's look for a black hole and see how it stores information. And how are black holes encoded in ADS-CFT? Well, there are thermal states of conformal field theories. So this is the kind of geometry that they would have. I mean, they would expand a bit more, but my screen was not big enough. So now I look at these quantities. I'm thinking, OK, this side here contains B and C. C will be the part that I will erase. B is the rest that I have, so I'll give access to my whole system to do recovery. I could try to do local recovery as well, but I won't in this case. And I mean, there's no proper subspace supporting a thermal state. This thermal state has support over the whole Hilbert space, so it's good that I have this isomorphism. And now I try to decode. If I want to keep the area of this black hole, sort of the global thermal entropy, and I have a Hamiltonian system, I actually need to scale the inverse temperature, so make the temperature lower as I make the system larger, because I have lower and lower energy states. So this is, like if I have a small system, this is how this spectrum for the free excitations would be. If I double the system size, and I want to keep the entropy, I need to lower the inverse temperature. And now I can look numerically at how this entropic quantity looks. And I see that if I scale it properly, the inverse temperature with n, so here's system size. Here the black line is plotting the thermal entropy. So I did this such that the thermal entropy sort of plateaus off to a constant. But I see that this conditional mutual information goes down quadratically, which means that I can correct a single erasure pretty well, 2 erasures, well, not a bit less well, 3 erasures, so on. But this is a really, I mean, I have to admit this. I mean, there's a really small entropy here, and there's a small system size, but this is trying to approach what holography people do, and it's trying to approach it in an order of regimes which is far off from what we need. Like, this is free theory. We're dealing with 13 bits of information, whereas if you want to get a meter or something, you need 10 to the 69 bits of information. So let me recap and compare the approaches that I've given you. Sort of, we had this tensor network construction, which had certain properties. The source channel code, which is the last one I proposed, which is somewhat explicit. It recovers boundary translation invariance up to the discrete nature if you have a model. This code properties from holographic geometries, I think of this more of an implicit framework that allows us to think what expectations we would get from holography. And yeah, I mean, some satisfy some properties, some others satisfy other properties. In the end, they're not the real holography, but what I feel is that we are sort of trying to use different tools to try to match different expectations. In the end, there's this big theory of quantum gravity, which has something to do with quantum error correction, and we're looking at different aspects. Or is it approximate? Is it operator error correction? Sort of the holographic area law, I mean, if you put it exactly, then it's in conflict with having CFT correlations in long distances. If you want an isomorphism, then it's not an isometry. And then it's not a subspace quantum error correcting code. If you want bulk locality, well, bulk locality is actually found to be incompatible with, this is what you'd expect in classical field theory. This is incompatible with diffeomorphism invariance, which is a principle for quantum gravity. So I mean, we're trying to figure out what the right elephant is, and maybe some further direction. So if we have a take-home message of what ADS-CFT is for us, quantum information theorists, is that this holographic area law is proposing to get the geometry from entanglement, certain states that have an entanglement structure that has a geometric analog, even though it's not the underlying geometry. And sort of these quantum error correcting tools provide toy models, but sometimes we need to extend these quantum error correcting tools and think about operator algebra error correction, think about approximate error correction, think about, I don't know, source coding. And, well, I haven't talked about this because I don't have progress yet, but ideally, we might use this holographic area law to try to get some advantage for us, for what this audience is interested in, which is making a quantum computer or doing quantum devices or quantum protocols. And I think there's a really neat structure that comes geometrically from this quantum error correcting codes that have a secret sharing scheme as an access structure. If we look at flat or positive curvatures, this is also something that we looked in the paper. We can get better rates. We can get constant rates. But the price we pay for that is that I would expect that the local Hamiltonian or the defining the theory the Hamiltonian defining the theory will be non-local, or the theory in the boundary will be non-local. So sort of the coding and checking becomes hard. Yeah, and yeah, with that, let me conclude and thank you for your time and your attention.